And thanks again for joining our webinar, Modular DC to DC Designs Done Right. So as we look at the contents of the webinar, we will actually go through the DC to DC modular design system process, essentially why we would select a DC to DC modular design versus a discrete design. And then we'll go through an example of selecting the DC to DCs for a particular power system. And then we will go through system integration and support circuitry needed to round out the power system. After we've selected the DC to DC converter modules, there may be support systems and circuitry needed to round out the power system. We'll look at power sourcing, characteristics and decoupling, input filter and stability analysis. Many power systems will need to meet EMI specifications and transient requirements, so we'll have to make sure that that is included within the DC to DC power system. Output filtering and transient requirements as well will be taken a look at. Special load characteristics and considerations. Many load systems are not purely resistive. A lot of them are very complex, and we'll take a look at what are the considerations for the DC to DC power system to handle these different loads. Safety and protection. A lot of the safety and protection considerations are not included within the DC to DC converters themselves, so we will have to add that externally. We will also take a look at current sharing and fault tolerant arrays. There are many systems out there that need to be reliable even when a module fails within the system. We have to maintain system operation, and we'll take a look at fault tolerant arrays and current sharing, and also signaling input and output characteristics for the DC to DC converters. Many of our power supplies today are very complex in terms of what can be done with them, in terms of monitoring them over line and load and during operation. So we'll take a look at that as well. So why would we select a DC to DC modular system? So many of our DC to DC modules that are made today are very high performance converters. So we have done the heavy lifting for you, so you don't have to worry about L's and C's and switching FETs and transformers to build the DC to DC converter section. We have done that for you. Many of the power systems that are very reliable, we have actually characterize the DC to DC converter over a temperature, shock and vibe. And they're very power dense as well, and high efficiency performing as well. And so the heavy lifting has been done for you. So you get a high performance DC to DC converter that can be used within your power system. Because the converters are very power dense, it gives you a high level of flexibility as well. Many times the power system is the last thing to be considered within the system. And sometimes there's very little space allowed for the power system. So having a small, power dense, and very efficient converter gives you a high level of flexibility when designing this power system. You can actually configure the power system in a very unique space. You may have an L-shaped configuration versus a rectangular configuration, or they can be chassis mounted. Using this modular system gives you that flexibility to configure this, your power system. The design and design time is also faster using a modular DC to DC approach. Because we have done the heavy lifting, a lot of the qualification for the DC to DC converter has already been done. So now you just configure the system and add the support circuitry needed for operation, whether you need output sequencing or redundancy. That is added external to the modular system. So when the development is much faster using the DC to DC modular system. So if we look at the design process. So once you have your power requirements, you do a high level definition of the output voltages and input voltage that's needed for the system. So you take a look at the number of output voltages that are needed at a high level, and then now you can place those and select the DC to DC converters that are needed to achieve the different output voltages and power levels that are needed. So you do a high level definition of the requirements. Then you just select the output, the architecture. So there are lots of different architectures that are available using the DC-to-DC modular system. You can actually choose a DC-to-DC converter that is directly processing power from the input voltage to your load voltage, or you can choose a intermediate bus architecture where you actually have a front-end module giving you an intermediate bus, say 48 or 12. Then you can distribute that to downstream non-isolated point of load converters because you have isolation on the front-end section. So here's where you can configure the architecture for your power system. And then lastly, consider the support circuitry needed to finalize the power system. This is where your EMI filtering would come into play, as well as special needs for the system, whether it be output voltage sequencing or hold-up requirements. That's the next step. Now, if we take a look at an example, here's an example where we have a 384 volt input, and we have a number of different output voltages. In this case, we've got 6 output voltages at different current levels. And then we make special notes regarding these output voltages. So here at our 120 amp 1.2 volt output, we need very tight regulation. And then this particular output, the 2.2 60 amp output, this is a voltage that might change in terms of its output characteristics. We may need to add current here. So we make special notes that are needed for the different output voltages. And so once we've tabulated the number of voltages and current levels that we need for the system, then we can actually lay out the architecture. Starting at the load, we will work backwards to select the DC-to-DC converters that can support the voltages and current levels that are needed for the system. So we actually lay out the loads and then select the different DC-to-DC converters that we have available. In this particular architecture, we've selected an intermediate bus down from our 384 volt source. And then we supply that 48 to PRMs and non-isolated point load converters to supply the downstream load voltages. And then in this last block down below, we can actually drive the DC-to-DC converters directly from the 384 volt architecture. Now, there's lots of different considerations here for selecting the architecture. You have to look at where isolation is needed. Do we need a negative voltage in the system? Does my 2.2 need to be isolated from my 3.3? Those are the considerations that we have to take into account when configuring the system architecture. And then once we've selected a basic block diagram, we can actually work backwards from the point of load to see how much power is needed by the upstream stage. So in this particular example, we've got an intermediate bus of 48 volts from our 384 volt source. And so we create the 384 volts using the efficiency information in the data sheets of the downstream DC-to-DC converters. We can actually determine how much current we need from the intermediate bus section. And because we are using the DC-to-DC converters, when system requirements change, we can adapt very easily. So if our 2.2 goes from 60 amps to 120 amps, we can actually add a block to accommodate that additional current demand. And then working backwards again, just to make sure that our front-end bus converter module or front-end intermediate bus section can deliver the proper amount of current, we work back from the efficiency again in the data sheets of the converters to make sure that our intermediate bus has enough current to feed the downstream DC-to-DC converters. Now, once the blocks are configured, using the DC-to-DC converter approach, we're not done, because the DC-to-DC converters in many cases do not include EMI support. And in that case, the EMI is needed external to the DC-to-DC converters. We also need to make sure that we have the right amount of protection for the converter in terms of fusing. And this is where all of the support circuitry that's needed for the DC to DC system or the power system is defined. In many cases, we may need support for dynamic loading in the system, whether it be a pulse load consideration. Redundancy, we need to configure the DC to DC converter for redundant operation, such that if one converter goes down, the system still maintains regulation. So when we look at a DC to DC converter, as a full system, this is the kind of the block diagram of everything that's needed for a particular DC to DC converter. So the DC to DC converter here will have a need for input transit protection. If you need mil standards for transits and surges. There's going to be EMI filter section, input filtering section to meet EMI specs. Safety. We have to consider the line impedance, because the line impedance plays a role in the stability of the DC to DC converter system now, so we'll see it later on. Our source impedance, we've got to consider the source impedance just to make sure our system is stable on the output section. Many systems need low output ripple just for proper operation of the load. So we may need to add an EMI filter or output filter to reduce output ripple. We also have to consider the line impedance from the DC to DC converter to the load, just to make sure that we don't get excessive voltage drops. And then the control. We've got to make sure that the DC to DC converter actually can regulate the DC voltage at the load. And many times there's remote sense lines that can be taken to the point of load, such that we regulate voltages and compensate for voltage drops at the output of the converter. So this is a complete picture of everything that's needed for the DC to DC converter system. And many times, some of these blocks can be incorporated into a modular design. There are some manufacturers that have an EMI filter for the DC to DC converter that is already packaged, so you don't have to design it yourself. So when we look at the source interconnections, when the DC to DC converter system, we have to look at the source that's feeding this DC to DC converter. And there are two sections, two characteristics that we need to take into account. One is the large signal characteristics, which is basically how much power is available from the source, the range of the input source, making sure that the high line and low line of the source can be accommodated by the DC to DC converter. Any special characteristics of the source in terms of its power delivery, line dropouts. Is there a need to survive or ride through line dropouts? Many of the mil standards require a 50 millisecond dropout requirement, and so we have to consider that for our source behavior. And then there's the small signal characteristic. Because the DC to DC converter is essentially a constant power device, it's considered a negative impedance. So when the input voltage rises, well, the input current will decrease. As the input voltage decreases, the input current will increase. And so that can have an effect on the stability of the DC to DC converter, if there's a high impedance source. So we've got to consider the small signal characteristics of the source, and just to make sure that our system is stable during operation. So let's take a look at input filtering. So as I mentioned before, many of the DC to DC converters have a high switching frequency characteristic, and such, they will have a noise signature that's emitted to the DC line at their input. And that noise signature has two characteristics: a common mode noise signature and a differential mode noise signature. The common mode noise signature is a noise or noise current that is present on both lines and they want to make their way back to the DC to DC converter through parasitic capacitance on the EMI ground plane beneath the DC to DC converter or the base plate of the DC to DC converter. So that noise signature is identical from both lines, positive N and minus N, to ground. And it's the parasitic capacitance in the system that carries this noise current. The differential mode noise. The differential mode noise from the DC to DC converter is common from positive N to negative N. So that noise is generated from the DC to DC converter, and it wants to circulate between the positive N and negative N, through the source. And so these are the noise systems that we need to mitigate to meet many of the EMI specifications. And the way this noise becomes a deterrent in the system is that noise is present on the DC lines. And there are other systems that may be on that DC line that are affected by the DC to DC converters. So this noise will, common mode and differential noise will be emitted onto this DC line and may affect communication systems and many control systems. And so a way to mitigate that noise is to add an EMI filter at the input of the DC to DC converter. So adding an EMI filter at the input of the DC to DC converter will keep the noise generated by the converter circulating close to the converter such that it does not get on to the DC bus and affect communication systems or control systems. And typically we can simplify the EMI design by placing one EMI filter at the input of each DC to DC converter. And this basically reduces the noise that's emitted into the system. So when we look at some of the specifications that are out there for EMI considerations, some of the mill systems will require EMI or mill standard 461 compliance for EMI filtering. Commercial standards have different EMI classes that this power system needs to meet. And so when we design a power system, we have to be aware of the EMI classifications or categories that the DC to DC power system needs to meet. And so we look at a EMI filter and noise mitigation technique. The filter typically has two components, a common mode element as well as a differential mode element. So the components in purple are the common mode noise elements. And again, the common mode noise elements are common from both of the inputs to the ground plane underneath the module. And so when we look at the common mode elements, these typically consist of a common mode choke and then Y caps to keep that current circulating close to the module, that high frequency current, common mode current circulating close to the module, such that it doesn't get out to the DC line. The differential mode components are typically, capacitors that are, connected from line to line. So positive N to minus N, and then we have some decoupling here to make sure our system is well damped. So this is the typical configuration of an EMI filter for a DC to DC converter. And as well as output Y caps as well are part of our common mode noise suppression system, because common mode currents on the output can be coupled to the input through interwinding capacitance of the DC to DC converter. So if we take a look at the different components that are used in our filtering system, the components need to be well damped to prevent peaking at the corner frequency of the system. If we take a look at a basic LC filter, shown here, we can see the characteristics out at frequency of this system. And we see at the corner frequency, we see this peaking. And this peaking can actually increase noise levels within the system if we don't have a well-dampened system. We see we've got good roll-off at high frequencies with this system, but we do have this peaking that we need to address. And one way to address this is to add a resistor in series with the inductor. Now, this this resistor will dampen and get rid of the peaking, but at the expense of our high frequency roll off. Another way to accommodate the peaking is to add a series dampening element in series with the resistor. If we add an inductor in series with the resistor, we will reduce the peaking, but we still have degradation of our roll off. And then the best method is to add a parallel damping combination, where we add a capacitor with a resistor to give us a dampening characteristic that will reduce the peaking as well as maintain our roll off for high frequencies. So when we have that filter, coupled with our DC to DC converter, we have to look at this system and make sure that the system is stable. So our source is actually an impedance that is presented to our DC to DC load system. And we need to make sure that this system is stable, because the DC to DC converter is a constant power device and a negative impedance. And so we need to make sure that the source with impedance doesn't cause a negative interaction with our load impedance or our DC to DC converter. And one of the ways to analyze this is to look at the ratio of my source impedance to my load impedance, or the input of the DC to DC converter. And if we look at our criteria for stability, assuming that each system is standalone stable, the ratio of the source impedance to the load impedance must be less than 1. And that will give us system stability. Now, if we look at this with our DC to DC converter, so the source impedance here is typically inductive. That'll give us our line inductance and possibly our input filtering. So that will be an inductive source. So it'll be low at low frequencies and then higher at higher frequencies. And our DC to DC converter, we'll consider that as a constant power and over frequency. And as we see here, as the frequencies increase, the source impedance will increase. And here we can actually get into a point where we created an unstable condition, where the input of the DC to DC converter can be unstable. We'll have startup issues and performance issues in case of a dynamic load. So one way to mitigate this is to add a capacitor to lower that source impedance. And so we add a capacitor at the input of the DC to DC converter, or at the output of the source, and a series resistance to make sure it's well damped. And this will actually lower the source impedance of such that I don't get a negative interaction between my source and my DC to DC converter. And if we take a look at the graph down below here, we can see the effects of adding that capacitor. So the red line here is actually the input source impedance of the DC to DC converter, and the green line is the performance of the capacitor. And as we add those two together, we see the source impedance is lowered from DC out to higher frequencies, such that there won't be a negative interaction between the source impedance and my DC to DC converter. So when we look at the input filter, when we add an input filter to meet EMI specifications, that filter now becomes part of my source subsystem. And so not only do I need to consider the line impedance, now I need to consider the impedance of my filter. And one of the ways we can analyze that is that as we look at this total source impedance, which includes my EMI filter, I've got to make sure that that is less than the impedance of my DC to DC converter. And one way to approximate the input impedance of the DC to DC converter is look at the input voltage in the low line of the input voltage. So if you've got a DC to DC converter that has to operate from 18 to 36, we evaluate this input impedance at 18 volts. So the minimum input voltage squared divided by the maximum power that the DC to DC converter will deliver will be my input impedance. And so now my source impedance has to be less than that impedance calculated, or the impedance seen by the input of the DC to DC converter. Now here's a graph that actually shows that there was a negative interaction between my source and my DC to DC converter at this point. And so by adding a decoupling capacitor at the input of the DC to DC converter, we can actually reduce that total source impedance such that you have good separation from the input impedance of the DC to DC converter down to our source impedance. Now, if we look at the output side, the output side, output filtering is typically used to reduce output ripple provided by the DC to DC converter. Because this is a switching device, you will see output ripple at the output of the DC to DC converter. And one way to reduce that output ripple is to add an LC filter. And so the considerations for the output filter, we have to look at the DIDT, because adding an inductor to the output of the DC to DC converter will hinder current delivery. If you have a high DIDT load, this inductor will actually drop the voltage across the capacitor and thus to the load. So we need to consider the value of this inductor in considerations with the high DIDT loads. And then for ripple reduction, we can actually just select components that have the cutoff frequency that we need to reduce the ripple to the value that we need. So when we take a look at laying out our DC to DC converter and filtering system, a lot of the layout characteristics can negatively affect the performance of my DC to DC converter and EMI filtering. So one of the ways the best practice to lay out a DC to DC converter and filter design is to have as linear a layout as possible, as well as having our bypass capacitance close to the DC to DC converter as possible. This minimizes the loop that you can have, and such that it keeps the circulating current close to the module. And if you have a large loop from our input capacitance to the DC to DC converter, that can actually radiate noise throughout the system, and that radiated noise will cause you to fail many radiated EMI specifications, or that radiated noise can become conducted noise somewhere else in the system. So keeping the bypass capacitance close to the DC to DC converter is one of the best practices in terms of laying out a DC to DC converter and EMI filter design. Also, keeping the Y capacitance close to the DC to DC converter, that minimizes the high frequency current loop that's flowing through these capacitors. And so keeping these capacitors close and keeping the loop from the positive end through the capacitor to the EMI ground or the base plate of the DC to DC converter is the most effective way of minimizing common mode noise. We also have to make sure that in the system, we don't route the output of the DC to DC converter near the input of the DC to DC converter, because the output of the converter has high switching frequency noise as well. And we want to make sure that that does not radiate around the filter to the input lines. I was working with one application where we actually bundled the cabling, input and output cabling, in the same bundle. And that caused us to fail EMI specifications because we were radiating onto that input cable from our output cables. And one of the fixes was just to add shielding and separation within the cable. When we lay out the PCB for our filtering components, we need to make sure that we don't create a layout that actually mitigates or reduces the effectiveness of our inductors and our common mode chokes. So here we have an example where the ground of the pad of the inductor was actually wide enough to create a parasitic capacitance from input to output. So now common mode currents can actually, or currents, high frequency currents, can use this parasitic path to radiate current noise around the inductor. And so one of the best practices is to make sure that our pads are wide enough such that we don't create a parasitic path from input to output or across the inductor. We need to make sure we take that same consideration with our common mode chokes. So in this example here, we've got a pad that actually creates a parasitic bridge such that currents can flow around the DC to DC converter, inductor, or the filter inductor. And so this is a proper layout where we don't create this parasitic capacitance. Another thing we need to consider when we select a filter is the rating or the capacitance value over temperature and over applied voltages. In some cases, we can actually reduce the amount of effective capacitance as voltage is applied to the capacitor. Here's a graph from Kemet where we actually look at the effective capacitance of a particular capacitor over applied voltage. As we see that this 6.3 volt cap, there's no derating or capacitance change at 0 volts. But as we apply voltage, there's a capacitance change. And this is something we need to consider when we design our DC to DC converter filter, or even if we're using it for decoupling capacitance. And in some cases, you can actually get a different performance by just changing the package size. So here's another package size where there's not as much deviation or change in the capacitance value versus applied voltage. Temperature is another factor we need to consider when selecting some of our components. In some cases, an electrolytic capacitor can change its characteristics quite a bit over temperature. Many cases, we need to design our DC to DC power system to meet -55 operation in case of military applications, or -40 in terms of industrial applications. So we need to make sure that the filtering components that we select have the proper value over the temperature range. And so here we see on this Evans cap at low temperatures, we see a significant drop in terms of the effective capacitance of this particular part. So that's something we need to take into account when designing our filtering system. Load considerations. So not all of the loads that are supplied or powered by the DC to DC converter are resistive. And so depending upon the load that you have, there can be an interaction with a control loop or an effect on the control loop of the DC to DC converter. So a resistive load has really no effect or effect of the transient response because it's a fixed resistor. It's constant in terms of its current demand. So in this case, we don't have an effect on the control loop or the transient response. But a more complex load, such as an inductor and capacitor and resistor, that can have an effect on our control loop response. Because now, especially if you're sensing it right at the point of load, this inductor and capacitor, that's within my control loop now. Now I have to take into account transient response, stability response, and other considerations that may affect the regulation at the DC to DC, at the point of load. Downstream DC to DC converters, that can possibly have an effect on the output of my DC to DC converter. Now I have another negative impedance on the output of my DC to DC converter. So this can possibly give us control loop effects where we have an unstable system. So that's something, a particular load where we really have to pay close attention to how the system is operating. Now, dealing with inductive loads, and sometimes our DC to DC converter is powering an inductive load, such as a motor or a relay. And an inductive load can, once the switch opens, this can actually create a negative transit back to the supply. And then we have to actually take into account that operation just to make sure that the output of our supply isn't damaged by this inductive load. And in many cases, a freewheeling diode is placed across the coil such that it keeps current flowing, such that you don't get a large inductive spike that comes back to the DC to DC converter or a negative spike to the converter. So this is an example of a load that it can actually affect the performance or the operation of the DC to DC converter. Post-load applications. In some applications, the load is on for a brief period of time and then off for a significant amount of time. So if we've got a load, a pulse load that is on for a 10% duty cycle, it is only demanding energy for 10% of the time. And so the rest of the time, the load is off. We see this in a pulse amplifier application where there's a huge slug of energy and then it's off for a relatively significant amount of time. Well, in many cases, system designers will design the DC to DC converter to supply that pulse load maximum. So if you have a 1,000-watt maximum pulse, the DC to DC converter system is designed to deliver 1,000 watts. And then that 1,000 watts is drawn from the source as well. So in a pulse load application, you can actually use what's called power averaging, where we store energy in bulk capacitance. And so now the DC to DC converter system can be sized to supply the average current to the capacitors, and the peak energy is actually drawn from the capacitors to the load. So a 1,000 amp load for a 10% duty cycle, all of the current for that 1,000 watt load is drawn from the capacitors, and the DC to DC converter just replenishes that energy for the next pulse. So here we see a 3 kilowatt load where it's on for 1 millisecond and off for 5 milliseconds. And so as the pulse occurs, all of the energy is drawn from the output capacitors. The voltage on the output capacitor drops. And then when the pulse is over, the DC to DC converter replenishes that energy to the original value before the next pulse comes along. And so here we've got the average power is only 500 watts, where the pulse peak power is 3 kilowatts. And so now using power averaging, the DC to DC converter system can be much smaller, can be much lighter, and much more cost effective than designing for the peak power. And the consideration for the DC to DC converter is that it must be a current limited and power limited device, because as the pulse comes along, it will deplenish the voltage on the cap. The converter will sense that the voltage has dropped, and now it has to be current limited, recharging that capacitor. And power limited, because at the very peak of the charge or end of the charge cycle, we don't want to overpower the DC to DC converter. But this still becomes a much more efficient, much smaller, much more power dense system when you make use of power averaging. Safety precautions. Many of the DC to DC converters are UL recognized, and in such they have a conditions of acceptability. And part of the conditions of acceptability is that there is typically a fuse required within the system close to the DC to DC converter. And many of the certificates are available at the manufacturer, so we can actually take a look at what's required to meet those UL conditions of acceptability. What type of fuse, the placement of the fuse, and just to make sure that we meet those conditions. So when we take a look at the fuse and the fuse placement, it's typically placed at the input of the DC to DC converter on the positive rail. And each converter will typically have their own fuse. And so we place, if a converter fails or a module fails, the fuse with an input short, the fuse will clear and protect the other modules within the system. And so one of the other considerations, where you have the ability to select your own fuse, one of the considerations is the current rating and temperature rating of the fuse. So we select the fuse current rating greater than the maximum operating current at the input of the current, the DC to DC converter. We want to make sure that the maximum current of the fuse isn't within the normal operating range of the DC to DC converter. So we take a look at the input line and then the maximum power, and we can select the maximum current of our fuse. So we look at the maximum power, the minimum line, since this is a negative impedance device, we look at the minimum DC line to select our maximum current rating. And then we add some derating on top of that to take into account for aging and protect against nuisance stripping. Now, the DC to DC converter system is typically designed to operate in a wide range of temperatures. In military applications, minus 55 to much higher temperatures. And so an additional derating must be taken into account for this temperature range. And these curves can be obtained from the fuse manufacturer. The voltage rating and interrupt current of the fuse. We've got to make sure that the fuse that we select, or that you can select, is rated for the application, the maximum DC to DC voltage within the application. So, yeah, and the fuse rating, we've got to make sure that there isn't any arcing that can take place. If you have a fuse that's rated for a much lower voltage in a high voltage application, once that fuse clears, you can have arcing over that fuse. And we've got to make sure that the fuse is rated for the DC voltage of the application. We also have to make sure that AC fuses are used in AC applications and DC fuses are used in DC applications. I squared T melting point of the fuse. This is taken into account when we have an application where the normal operation will see current surges above the maximum current rating of the fuse. And you'll see this when you have module inrush at startup, charging capacitance, and any transits that may be introduced to the system. So the fuse has to withstand this momentary, current excursions above its maximum. And we can actually add a derating factor or a pulse factor when selecting this fuse. Additional fuse considerations. The fuse should be placed in the positive input or the non-grounded side of the DC to DC converter. And the fuse is really there to protect against fire and further damage, thermal damage, in the case of a fault. The fuse really isn't there to protect the DC to DC converter, because once the fuse clears, if the fuse is selected properly, something has gone wrong within the system. And so the fuse clearing will prevent, that system or that failed system from overheating or from further damage being done to this failed site. And so we have to make sure that the current conductors or traces leading to the system are properly sized to carry the current before the fuse clears. Transients and spikes and surges. So many of the systems have to meet, transients and spike conditions. And the transients, the spikes and surges are treated differently. Spikes are typically shorter in duration and higher in voltage. So if we look at this particular specification, mil standard 1275, this is typically designed for a 28 volt DC line. So a spike is a very short duration, in this case, 70 microseconds, with a maximum voltage of 250 volts. A surge is typically longer in duration, lower in magnitude. And so here we've got a 50 millisecond surge at 100 volts. And so there's different ways of suppressing or mitigating the effects of a transient, surge, and spike. And one way is to add a two-stage filtering section or transient protection circuit. In one stage, we have TVSs, transient voltage suppressors, that handle the fast transients. And these can handle transients on the order of 100 microseconds. And these can handle quite a bit of energy. So the transient protection voltage suppressors, they can handle the fast, high voltage spikes. And we have to select the value of these such that the knee of the transient voltage suppressor isn't within the normal operating range of my DC to DC converter. We don't want this clipping or trying to draw current during the normal mode of operation, but it has to be sized such that it can actually clip the transient to stay within the normal operating range or the transient operating range of the downstream DC to DC converter. So this is a shunting method of suppressing a transient spike. So when we have longer transients, we have to select a series element. And so for a surge, we select a series FET or a series Q1 to actually drop voltage across the line, such that the DC to DC converter downstream is protected. And in this case, we detect the input voltage and then put Q1 in a linear range such that it drops voltage and protects the downstream DC to DC converter. Now, when we select this clipping method, we've got to make sure that Q1 is sized such that we stay within the SOA curves of the FET of Q1. And so, because the system will continue to draw current and stay within operation. So now the source current is being drawn through Q1 while it's dropping voltage. So that's 50 milliseconds or 10 milliseconds. So we've got to make sure that Q1 is sized to stay within the operating range or safe operating area. And Q1 is always in circuit, so it's best to choose a FET that has a very low RDS on because it is always within circuit. Current sharing and fault tolerant arrays. There are many systems that have to be operational even during a fault of a DC to DC converter. In high rail applications, we've got to make sure that the system stays up even when there's a fault on the DC to DC converter. And so this is done by actually creating redundant arrays of DC to DC converters. So here we have a converter 1 and converter 2 are both paralleled to supply current to the load. If converter 1 goes down, converter 2 is sized to take over the load and maintain operation. Now, one of the best ways to configure the system is to make sure that DC to DC converter 1 and converter 2 are current sharing. This way, we have a better transition from going from 50% load to full load, then going from no load to full load. And so, because once a converter goes offline, the other converter that's still operating has to support the load. And as that transient occurs, if they're both current sharing, you get a better transient response at the load. Also, current sharing of converters increases system reliability. We will see that they'll both run at cooler temperatures, and the MTBF of the system will be much better than if one converter were operating, taking the full load, and just waiting for the other converter to drop off. There's a couple of different current sharing methods for the DC to DC converters. One is a droop sharing method, where as the load increases, the output voltage tends to decrease. And then the other converter that's online will see that decrease in voltage, and they will pick up its current delivery. Another is an active current sharing method, where there's a communication between the two converters that facilitates current sharing. One of the effects of having two converters within the system is that the converters can develop a beat frequency between them. And this beat frequency is the difference between the switching frequency of the two different DC to DC converters. Because of component tolerances, even identical converters will have a slightly different switching frequency. And that switching frequency can cause currents to circulate between the two different converters, their inputs, as well as their outputs. And this circulating current will present itself as a beat frequency to the line and to the load. And this beat frequency is basically the difference between the switching frequency of the two different converters. And in some cases, this beat frequency can be difficult to filter and cause EMI failures. And so one way to mitigate a beat frequency is to add an LC filter at the input of the DC to DC converter, as well as at the output, to reduce output beat frequencies. In this configuration, we reduce the effects of the difference in the switching frequency of the converter such that we mitigate and eliminate or reduce that beat frequency seen by the source and seen by the load. In redundant applications, the system has to be up and running even when there's an input short or an output short of the DC to DC converter. As we've seen before, an input short can be handled by a fuse at the input of the converter. There's enough energy from the source to clear the fuse, such that if converter 1 in this application or in this drawing, if converter 1 has an input short, it will clear its fuse, and then converter 2 will be unaffected. It can still operate. Now, in the case of output shorts, O-ring diodes are typically used or can be used to protect the output of the DC to DC converter from drawing current in the case of a short of its neighbor. So if converter 1 has an output short, D1 is reverse bias, and so converter 2 won't feed the short. It will support the load during an output short. Now, the diodes can create a significant power loss within the system. So in some cases, you can actually use O-ring sets on the output of the DC to DC converter. There's circuitry that will bias the set in the on position, and such that when an output short occurs, the Q1 set here is turned off, and so it protects the DC to DC converter or the remaining DC to DC converter from feeding that short. Now, it adds a level of complexity, but as we can see, it will actually reduce the power losses within the system, because now we just have the RDS on of the set times the current instead of a fixed voltage drop. And in some cases, this can be a significant power savings within the system, because these sets can be parallel to be in the milliohm range versus a 0.3 volt drop, even with a Schottky diode. It adds a level of complexity, but it's typically a huge power savings. Signaling. Many of our converters today are very feature-rich in terms of what can be done with them. There's control interfaces, analog and digital. In some cases, the DC to DC converter, you can actually control the output voltage via a trim pin, or disable the converter, and monitor the converter for health, fault status and temperature as well. So these are analog features within the DC to DC converter. And some converters have digital interface where you can actually communicate to the converter and poll it for output voltage set point, enabling and disabling the converter. Fault protection or telemetry. We can actually get information from the DC to DC converter and use that within the system by just communicating via PM bus or some other protocol. So when we actually use those systems, we've got to make sure that those communication systems are tied to signal grounds or very low noise grounds, such that that communication isn't corrupted by switching noise. And so one of the ways to regulate voltage over some distance or over a line impedance is to use the sense lines of the DC to DC converter. We can actually run those sense lines to the DC to DC converter and create a Kelvin connection such that we can compensate, the DC to DC converter can compensate for line drops. And this can be significant in some cases, several feet. So the DC to DC converter can compensate for these line drops. And we have to make sure that we consider the stability of the system once this is done. And another method of regulating the output voltage remotely is to use an external device that will sense the voltage at the load and then control the DC to DC converter to regulate the voltage across at the point of load and compensate for voltage drops through the line impedance. So signal grounding. So when we do our signal grounding, again, we've got to make sure that we avoid corrupting that signal by tying the ground to high frequency ground return or power lines. So those power lines will contain high frequency noise, which can actually corrupt the communication, to a controller and corrupted data that is sent back from the power supply. So we've got to make sure that those signals are tied to a low noise ground plane or signal ground within the system. And typically the DC to DC converter will have a signal pin that's a Kelvin connection to the minus N of the converter. And this is the best place to tie the signal ground for control signals. And power ground is just left for delivering power to the load and receiving power from the source. So we've got to make sure that those two grounds are separated, because we don't want to corrupt the signals that we're using for communication to the supply. Well, thank you very much. That concludes the webinar. You can actually submit questions, in your question box. And if we don't get to the questions online here or live here, we will email you those responses to those questions at a later date. And again, we're going to submit or email this presentation to all of the attendees after this presentation. So Jackie, are there any questions?
Thanks, David. Let me check, and we do have a few questions. We have 2 minutes, so let me get right to the first one. The first question is, which ground should the Y caps tie to?
That's a good question. So the Y caps are there to suppress common mode noise. And the common mode noise is generated from the switching devices to the base plate or the ground plane underneath the module. And so the Y caps should be tied to the base plate of the DC to DC converter. And if the converter doesn't have a base plate, it should be tied to the EMI ground that's underneath the DC to DC converter. And again, the Y cap should be placed with a very short loop from power lines to that EMI ground or base plate.
Okay. Next question. Looking at the source impedance, which frequency range should be considered?
Okay, yes, I've had that question posed to me several times. So when we look at the source impedance, we want to make sure that that is low from DC out to the crossover frequency of the DC to DC converter times 2. In many cases, if you're designing the DC to DC converter, you can determine the crossover frequency, or the DC to DC converter manufacturer can give you that crossover frequency, and then just multiply by 2, and that's the frequency range that you should consider. In many cases, that frequency range or crossover frequency, times 2 can be in the 50 kilohertz to 100 kilohertz.
Okay. Well, unfortunately, we're out of time. Thank you, David, and thank you, everyone, for attending today's webinar. If we didn't get to your question, we will email you individually about that. And once you leave today's webinar, you'll receive a survey on the presentation. We would appreciate it if you would complete that and give us your feedback. And everyone will also receive a follow-up email with a link to the recording of today's webinar. On behalf of Vicor and David Barry, thank you for joining us, and have a great rest of your day.